All right, so what we're going to look at today are properties, behaviors, etc. of ionic and molecular compounds, and we're also going to look at the behaviors and properties of acids and bases. Okay, that is going to allow us, okay, everything that's in this lesson is going to allow us on Wednesday to be able to look at these unknown compounds, okay, run a few simple tests on them, and then be able to pick out their identities from a list. Okay, so for example, one of those compounds is sodium chloride. Okay, you'd have to be able to look at it, okay, run a few simple tests, and identify whichever one of those things is sodium chloride. Okay, now I know you're probably all thinking, gee, that one seems pretty easy. I know what salt looks like. Yeah, well, sugar's one of them too. Okay, and they look pretty close to how each other look when you put them side by side. Okay, there'll be a couple of tests that'll make it possible to separate the two. Taste is not one of the tests. Okay, there are a couple of these compounds that they would be the last thing you taste if you tasted them, because they would literally burn your tongue off. Okay, so taste tests are out. Okay, those are not one of the tests. Okay. Neither is picking them up and playing with them. Okay, there's no potassium permanganate in their bodies. Okay, some of them are pretty corrosive, and unless you're looking to remove your fingerprints to commit a crime, okay, probably not what we want you to do. Okay, all right. So we're going to learn the properties of compounds, and we're going to look at how those can be used to identify a compound if we had it as an unknown. Okay, there are two kinds of properties that any element, compound, material can have. They can have physical properties, and they can have chemical properties. We're focusing today and this week on physical properties. Okay, so physical properties are, the obvious things that you can see when you are, observing something. So that would be things like color, density, melting point, okay, state, okay, yeah, lots of different things. Solubility, okay, how well does it dissolve in water? Something we call aqueous conductivity. So does a solution of them in water conduct electricity or not? Okay, things like that are all things that we'd be testing. pH, okay, is it an acid or a base? Okay, all of those things are physical properties, and we'll be running tests to find those for each of these unknown compounds. Okay, so I would say, have the list there of physical properties. Okay, we also said solubility, okay, pH, okay, oh, another one, odor. Incidentally, if you need to smell an unknown compound, is there a technique for that? Okay, we call that wafting. Okay, you don't put it right up to your nose and go, okay, because again, some of these things are, well, fairly powdery. Okay, and if you were to get them in your sinuses, could be unpleasant. Okay, so we wouldn't want that to happen. Okay, so wafting, just doing this. Okay, I found that out the hard way. Okay, as like a second-year teacher, I was making materials for a lab, and I had a concentrated thing of hydrochloric acid open, and I sneezed. And what do you do right after you sneeze? Inhale sharply, right? Okay, so I sneeze, and my face is right over top of them. Boom, flat on my back, blood coming out of my nose. Okay, yeah, I should have seen my colleague's face when I came in and found me. Okay, so we definitely don't want to be snorting any of these compounds. Okay, just wafting will do. I made them concentrated enough that they've got a smell, you'll know. Okay, they will have a distinctive smell. All right, questions on the physical properties. Okay, we will talk about chemical properties later on in the unit. chemical properties are basically, do you react with this? Do you react with that? Okay, stuff like that. Okay, so things to know about ionic compounds. Okay, I mentioned earlier that we don't want to call like sodium chloride salt, because salt is a general term for any crystalline substance that is ionic. Okay, so ionic compounds typically exist as crystalline solids or salts, okay, at room temperature, okay, and they have very high melting points. So that entire sentence or point, okay, you should definitely have somewhere. I would also copy the entire second point, okay? And then I'll give you a few minutes just to do that, and then we'll talk about what they mean. Okay, so have both in your notes, and then I'll talk about it here. Okay, so all ionic compounds are crystalline solids at room temperature. Does that mean that all crystalline solids are ionic compounds? No. Okay, sugar would be a prime example. Okay, sugar is a crystalline solid at room temperature, but it's molecular. Okay, so just because one is true, all ionic ones are, it doesn't mean the reverse is. Okay, so if you're looking at compounds in our lab, okay, so let's say you're looking at this one. Okay, does it sound salty, crystalline? Okay, versus like one like this. Okay, that's like flaky. Okay, definitely not crystalline. And I know it's safe to touch this one because obviously I made them. Okay, in fact, it doesn't feel crystalline at all. It's almost sticky. Okay, so probably not ionic then. Agreed? Okay, so some things you can tell kind of by looking at them. Okay, that they wouldn't be. But if something is a crystalline solid, then you got to have a way to separate it. Okay, and make sure that it's ionic. That's where this point is important. Okay. Ionic compounds, when you dissolve them in water, that solution will conduct electricity. That's not true for molecular compounds. So if you dissolve sugar in water, it won't conduct electricity. But if you dissolve salt in water, it will. Okay? Reason for that is, when you put salt into water and it dissolves, it breaks up into positively charged sodium ions and negatively charged chlorine ions. Okay? Because there are now charged particles, it is possible for electrons to flow through that solution. If there are no charged particles in the solution, then electrons can't transfer from charged particle to charged particle. Okay, is that making some sense? Okay, so would distilled water conduct electricity? No. Distilled water will not conduct electricity because water is not going to split up into hydrogen and oxygen ions. Okay? That means anything you dissolve in distilled water, okay, is either going to break into charged particles like salt and then conduct electricity, or just dissolve and not. Okay? So if I dissolve sugar in water, I haven't put any charged particles in the solution, and as a result, it won't conduct. Would that be the best way to separate between sugar and salt in your lab? I would say so, because they look a lot alike. Okay? They're both soluble in water, so they'll both dissolve. Okay? They probably both have a similar pH. Neither one of them is heavily acidic or basic. Right? That would be their only difference, right? Because we can't taste them. Obviously, a taste test would separate them, but we're not allowed to do that. Okay? Making some sense? Okay. So this one here, okay, this test will always indicate ionic, that would be conducts, okay, or molecular, okay, non-conductive. Okay, and tomorrow I'll show you the little meter that we use to test that with. Basically a 9-volt battery with 2 leads coming off of it. Okay, and we'll properties that tell you how much it conducts. Pretty simple piece of equipment to use. Okay, now, some of these have distinctive colors, right? This one's blue, okay? Got one that's kind of orangish red, okay? One that's pretty bright green, okay? And then there's a whole bunch that are just white, okay? No. Okay, is that definitely crystalline? Okay. Some metals, when they're in an ionic compound, always generate a certain color. So could color help you to identify something as, oh, that one's a nickel-containing compound versus that's a sodium compound? It definitely could. Okay, so we're going to learn those colors. They're on the next slide here, okay, because those will be super useful for identifying several of your unknowns in the lab on Wednesday. Okay, so anything that contains copper, okay, will create a blue salt and also a blue solution, obviously, when you dissolve it. Okay. Nickel-containing compounds are always green. Okay. And cobalt-containing compounds, they vary, but they're generally orange, red, pink. Okay? So, would that be useful for that, and that? Right? Does that mean you don't do any other tests on these? You still run all the tests. I mean, you got to confirm. There's other things that could be colored. Okay, we just need to know. Okay, for sure. Okay, questions on that slide? Everybody good there? All right, now, molecular compounds. Okay, molecular compounds can be solids, liquids, or gases at room temperature. Okay, it all depends on their melting points and their boiling points, which tend to be a lot lower than ionic compounds. Ionic compounds typically have melting points in the several hundreds of degrees. Okay, whereas molecular compounds typically, melt, pretty low, right? Like, for water, for example, it's 0. Okay, butter, right? That's a molecular compound. You put that in your hand, it'll start to melt. Okay, things like that. Sugar, you generally can heat it up to about, 85, 90 degrees Celsius, and it's going to be starting to melt as well. Okay, so they typically have lower or melting or boiling points. They're not usually as soluble. Okay, like sugar, sure, it'll dissolve in water, but you can't dissolve nearly as much sugar as you can salt. Okay, salt tends to be quite a bit more soluble. Okay, and of course, any solutions you make will not conduct electricity because they are not separating into charged particles. All right, so I would say everything on that slide, that's going to be important when you're doing your analysis for the lab, okay, that we do on Wednesday. Okay, so could this rule be helpful? If all ionic compounds are crystalline solids at room temperature, and you have a liquid as an unknown, yeah, would it be not ionic then? Yes. Okay, if one of your unknowns is a liquid, it can't be ionic. Ionic compounds at room temperature are crystalline solids. Okay, so that's out. That would really help you eliminate, okay, a lot of the possible unknowns. If you look at it and go, okay, that's a liquid. So It can only be these ones in my list of unknowns. Okay, and probably not sugar, because sugar is generally not a liquid at room temperature, right? But it's just little physical properties. That's the process I want you to be able to go through, okay, when you're trying to figure out what everything is. Okay. Two of your unknowns on Wednesday are water and ethanol. Okay? So ethanol is the active ingredient in hand sanitizer. Since you guys have lived through COVID, I know you know what that smells like. Okay? What does water smell like? Nothing, yeah. Unless it's like gross water, and then it might have like a ugly smell. But this is going to be nice distilled water, it'll be nice and clean. Okay? So it won't have a smell. Would that be a good way to tell the two apart? Yeah. Because otherwise, are they going to behave pretty much the same? Right? They're both going to be a clear liquid. Does alcohol dissolve in water? Like if you were to pour like rubbing alcohol into a glass of water, would it sit on top or would it just disappear? It would disappear, yeah. Okay. You guys aren't old enough to know this, but that's how mixed drinks work. Like if you pour booze into something else, it dissolves, it doesn't sit on top. Okay, that would not work for a lot of mixology. Okay, so yeah, alcohol absolutely dissolves in water. Okay, so it'd be hard to tell those apart. Okay, neither one's going to conduct electricity. Their pHs are pretty close. Water's neutral. Okay, ethanol might be a little off of neutral. Okay, but otherwise they're going to be pretty much the same except for their odor. Okay? Again, we're identifying these with their physical properties. Okay? If I waft one of those jars and I don't smell anything, and then I waft the other jar and it brings back memories of being in isolation at home, okay, you know which one's which. Agreed? All right, molecular compounds which are soluble in water do not produce, generally, colored solutions. Okay? They are usually clear. Okay? Okay, questions there? All right, let's talk acids and bases here now. Okay, acids and bases kind of fall into two categories: strong acids and strong bases, okay, or weak acids and weak bases. So citric acid, which would be in orange juice, grapefruit juice, lemonade, okay, all those kind of things, that's a weak acid. All right. Strong acids, and weak acids. Okay, strong acids are all ionic compounds. Okay, and they are ionic compounds, okay, that have hydrogen acting as the metal. Okay, so they'll have an H plus ion in them. So okay, anything that starts with H, okay, and then has a non-metal behind it is going to be a strong acid. And if you're thinking water right now, put that aside. I'll explain why water is not in a minute. Okay. Okay, so since all acids have hydrogen acting as a metal, they are also, okay, strong acids are ionic compounds. Okay, they will be highly soluble, so they will dissolve very easily, and they will be your best conductors in the lab. Okay, when you put the little conductivity meter in, it'll flash 9 or 10 out of 10. Okay, so this stuff here, would that be an acid? Yeah. It's got hydrogen acting as a metal. It's attached to a non-metal. It's an ionic compound. That is hydrochloric acid. Okay, your body actually naturally produces it. It's what's in your stomach. Okay, it helps you to digest food. Okay, it can also cause ulcers. Right? It can cause a chemical burn on the inside of your stomach. Okay. What about this stuff? Would that also be an acid? Which one would be stronger? The second one. Okay, here's what decides how strong an acid is. How many hydrogens will end up in solution when it dissolves? Okay, if I dissolve hydrogen chloride, every hydrogen chloride donates 1 hydrogen plus. If I dissolve H2S, every H2S gives me 2. So it'll be a stronger acid. Okay? If anyone is looking at going into like oil field stuff, okay, you have to take an H2S qualification. Okay? It's basically a safety course that you have to take because hydrogen sulfide, okay, can be an associated gas with drilling. It can come out, and if you breathe it in, okay, you're basically breathing in an acidic vapor, and it will dissolve your sinuses, lungs, very, very dangerous stuff. Okay, so you have to know how to use all the proper protective equipment, okay, things like that. So if you know somebody who's works on rigs or something like that, they probably have taken their H2S course. Okay. All right, what about this one? Even stronger? Yeah. Okay. Nitric acid is very, very dangerous stuff. Okay. Even the vapors can cause chemical burns in a matter of minutes. Okay. So you have to be very, very careful with that stuff. So the more hydrogens that can be donated, the stronger that acid will be. Okay. Everyone with me there? So if you see something in your list of unknowns, okay, and it starts with hydrogen, right, and it's ionic, would it have a low pH? Yeah, because acids have pHs below 7, right? So if you're doing a bunch of tests and one of yours comes out, oh my gosh, it turned my litmus paper like bright red, okay? That would be an acid. You just got to look down your list of unknowns for something that is an ionic compound starting with hydrogen. Okay? Questions there? All right, obviously we will not be doing this, okay? Acids taste sour or tart, okay? Yeah, I mean, we've all, eaten a lemon or a lime or a grapefruit, right? They're sour, okay? Acids are typically sour, even like vinegar, for example, okay? Vinegar is kind of like a tart, sour flavor, okay? Vinegar is an acid, okay? It's actually an ionic compound, okay? But we write it like this. Okay? This is the positively charged ion, and that's the negatively charged ion. Okay? Called acetate, which is why vinegar is often called acetic acid. Okay? It is hydrogen acetate. Right? We have hydrogen acetate in the lab that is glacial. That means it is 100% acetic acid. The vinegar you buy in the store is 5%. Okay? 5% acetic acid, 95% water. Okay? Don't put the acetic acid from the lab on your fries. It will eat them for you. Okay? It is literally that corrosive. Okay? All right. Questions on that? Okay. Bases. Very similar, but on the opposite side of the pH scale. Right? Strong acids are also ionic compounds. They will dissolve very easily, and their solutions will conduct electricity. They will also be some of the best conductors in your lab on Wednesday. can strong bases be just as dangerous as strong acids? Absolutely. Okay? Strong bases can be just as corrosive or even more so, okay, than a strong acid can. Okay? They're very, very corrosive. But it's because they have a very high pH. Okay? The end result looks the same. Something gets dissolved or eaten, okay, by a strong acid or a strong base, which is why that stuff, what's that stuff called? Sodium hydroxide. Okay? This is the active ingredient in oven cleaner. Okay, so if you've ever sprayed the white foamy stuff on the inside of your oven, okay, the active ingredient in that is sodium hydroxide. Okay, and if you like smell that, like they always say, use in a well-ventilated area, you know, don't get too close when you spray it, it'll curl your nose hairs. Okay, and it has a very distinctive smell, but it's highly corrosive. That's why it can eat the crud off that's baked on the inside of your oven. So which would be stronger? This or that? Yeah, the second one. Okay. Calcium hydroxide is also commonly referred to as lime. Okay. If you've ever watched any like of those like murder shows, you know, they're on like the Discovery, you know, and whatever. That's the stuff that people who commit murders will use to dissolve bodies. Okay, like they'll put a bunch of lime on the body and it will literally destroy like DNA. It'll dissolve the body to basically nothing. Okay, I'm not, by the way, telling you to hide evidence of your crimes or anything. I'm just telling you this is something that they also will put it in like if you've ever been to a pit toilet. Okay, right. So the ones that just have a hole underneath where all the stuff goes. Okay, they'll put lime in there to kill a lot of the bacteria and stuff like that that would grow in there, okay, and keep it from smelling, okay, stuff like that. Okay, so bases have hydroxide ions in them, okay, so they'll end in OH. They'll start with a metal and they'll end in OH. That will be a strong base. Okay, what's that stuff? Okay, what's the name of this polyatomic ion? I know you all read it, someone can say it. HCO3? Nope, that's this stuff. Okay, HCO3, right up here. Okay, that stuff is sodium hydrogen carbonate. You probably have a box of it in your fridge. What is it? You were right.
Baking soda.
Baking soda. Is baking soda a base? It is. But it's not a strong base because it doesn't end in OH. Okay, strong bases end in OH. Doesn't mean that other things can't be basic. They're just not going to be a strong base. Sodium hydrogen carbonate, pH is around like 9, okay, 10, somewhere in there. It's not a strong base, okay, like an equal amount of sodium hydroxide would be. All right? So bases, not that we would do this, typically taste bitter. Okay, if you've ever like tasted baking soda, it's very bitter. Okay, if you ever had your mouth washed out with soap as a kid, okay, I don't know if parents still do that, but they did when I was a kid. Okay, you know, it tastes bitter. Why? Because it's got lye in it. Okay, it's one of the active ingredients in soap. It's a strong base. It tastes bitter. Okay, helps cut oils on skin. That's why we use it. Okay. All right, questions on bases. Okay, so they're going to be good conductors, they're going to be ionic, and they're always going to be an ionic compound that ends in OH. Okay. All right. Then, in the lab, what we're going to do is we're going to run a kind of a battery of tests. Okay, so you'll get a small depression plate, which I'll show you tomorrow. Okay, it's not sad. Okay, it's just a plate that's got little holes in it, little dips, depressions. Okay, and you're going to put the unknowns in there, and then we're going to, kind of record our observations about them. Okay, well, this one was a green crystalline solid that didn't have any smell. Okay, whatever. And then you'll add some water to it to see if it dissolves. You'll also record the temperature while it dissolves to see if there's any temperature change. Okay? Then you'll test the conductivity of that solution, and then you'll finally dip a piece of pH paper in it and record the pH off of the side of the jar. Okay, pretty simple lab. You're going to be testing all of those things in the lab. Okay, and then at the end, you'll tell me, okay, substance A was, sodium chloride. Substance B was water. Substance C was nickel 2 chloride or whatever. Okay, making sense? All right, I'm going to put a few compounds up on the board here. Naming and writing formulas practice. Okay, so write these ones down. Okay, guys, I'll give you a few minutes on those. Obviously, if I give you the formula, I want the name. Hey, if I give you the name, I want the formula. All right, give you a few minutes on that. All right, let's go through a few of these here. Okay, so for number 1, ionic or molecular? Ionic, yeah, sodium is a metal, okay? It's with phosphorus, so we follow the naming rules, okay? Sodium, phosphide, okay? No prefixes. Number 2, I've got sulfur and fluorine, both non-metals, so this is molecular. Okay, so molecular rules say prefixes. Do I need a prefix on the first one? Which one? Tri. Right, so we got tri-sulfur, UR, okay? And it's with fluorine, so what prefix do I use? Di. All right, for number 3, okay, I've got cobalt and oxygen, right? Ionic or molecular? Ionic, okay, so I follow the ionic rules, okay? It's cobalt, it's with oxygen. Does it need a Roman numeral? Yeah, it does. Okay, cobalt can be a 2 or a 3. All right, so as always, I look to the non-metal. Oxygen's always a -2. -2 times 3 gives me 6 negative charges that have to be balanced off by 6 positive charges coming from only 2 cobalt. 6 divided by 2 is +3. This is cobalt Roman numeral 3. Okay. And then for number 4, I've got calcium with a polyatomic ion sulfate, okay? So ionic compound, I've got calcium sulfate. Okay. Is the last one ionic or molecular? It's ionic, yeah, lead is a metal, okay? And it's got a polyatomic ion in it. So follow the naming rules. I write the metal, I write the non-metal, nitrate. Okay, does this one need a Roman numeral? Yeah, lead can be a 2 or a 4. Okay, so nitrate, according to my chart, is a -1. How many nitrates are there? 2. All right, so we got 2 negative charges. I've got to get 2 positive charges, and I only have 1 lead to do it with. So that lead has a charge of 2. Lead to nitrate. Okay, guys, only way to get good at these is to practice. Okay, so if this part of the quiz did not go well, that just tells you need to practice more. Okay, or come in and get some help from me. Okay, it's probably some little simple thing, okay? But that part of it is on you. Okay, all right, number 6. Okay, we got lithium nitride, ionic or molecular? Ionic. Okay, lithium is a metal. All right, so we got Li, okay, and it's a +1. Nitrogen is a -3. Drop and swap. Okay, Li3N. Diphosphorus heptachloride, ionic or molecular? Molecular, both non-metals, plus it's full of prefixes. Okay, so P2, that's what di means. What does hepta mean? 7. Yeah, P2Cl7. All right, magnesium carbonate, ionic or molecular? Okay. Okay, so 2+, magnesium is a 2+, carbonate is CO3. It's a 2-. Did those already work out? I mean, I could drop and swap them, but then I'd have to reduce them down to 1 and 1 anyway. Okay, if they already add up to 0, you're good the way it's written. Okay, number 9, tin 4 phosphide. Okay, so SN, the 4 tells me what charge to use. Phosphorus, always a -3. Drop and swap. Okay, and then our last one, okay, iron 3 sulfide. Okay, so Fe, Roman numeral says use the 3+. It's with sulfur. That's a -2. Drop and swap. Questions on any of those? Okay, so as I said earlier, this week we'll still have naming on the quiz. Maybe even next week. Reason? It's a pretty fundamental skill that you have to have in order to write reactions properly. It is virtually impossible to get reactions to work if you can't write the formulas and the names properly. Okay, so it is something you have to work on. So, remainder of class, because we still have 14 minutes, okay, I want you working on those worksheets that I handed out last week. Okay, work on those. If you're having trouble, let me know. I'll come around and give you a hand. And then tomorrow we'll talk about lab reports and do the pre-lab, and maybe have a little more time for naming.